This is Sleepy Space, a slow space story to help you fall asleep. Light takes time to travel. That simple fact means every time you look up at the night sky, you are looking backward through time. And when astronomers recently used that fact to look deeper into the past than ever before, they found something that should not exist. The light from the nearest star beyond our sun left its surface more than 4 years ago. The glow from distant galaxies began its journey millions, sometimes billions of years before humans ever appeared. The farther we look into space, the deeper we peer into cosmic history. Distance and time are inseparable. To see far is to see long ago. This is not metaphor. It is the fundamental nature of observation across cosmic distances. Space is not just a place we look through. It is a record of time itself, layered and stretched across the universe. The James Webb Space Telescope was designed to exploit this reality. Positioned nearly 1 million miles from Earth, it orbits a gravitational balance point between our planet and the Sun, far from their heat and glare. Its mirror spans more than 20 feet across, composed of 18 precisely aligned hexagonal segments, each coated in a thin layer of gold. That gold is not decorative. It reflects infrared light with extraordinary efficiency, allowing Webb to detect wavelengths stretched and reddened by the expansion of the universe. Webb's mission was clearly defined from the start. Observe the first galaxies. Study how stars formed. Look back to the era when the universe was young, before familiar structures fully existed. To accomplish this, astronomers conducted what are known as deep field observations. They aimed the telescope at regions of sky that appeared almost completely empty and allowed it to gather light for long periods of time. What looks like darkness to human eyes slowly reveals itself. Thousands of galaxies emerge. Some are relatively nearby, their light only millions of years old. Others are so distant that their photons traveled more than 13 billion years before reaching Webb's mirror. When we observe galaxies at those distances, we see the universe as it once was. Not billions of years into its life, but near the beginning itself. Sometimes when it was less than 1 billion years old. Sometimes only a few 100 million years after the moment of creation. For decades, theory told us what we should expect to find there. In the early universe, shortly after the Big Bang, conditions were simple. Mostly hydrogen, some helium, vast clouds of diffuse gas drifting through expanding space. Gravity slowly pulled this material together, forming the first stars. Those stars lived brief, violent lives, exploding and enriching their surroundings with heavier elements. Over immense spans of time, small collections of stars merged, gradually assembling into larger systems. The key word in all of this is slowly. Galaxy formation, according to our best understanding of physics, is a patient process. Small things form first. Larger structures assemble later. Complexity emerges step by step, like a city growing from individual bricks, then houses, then neighborhoods, over centuries. When Webb turned its gaze toward the earliest epochs, astronomers expected to see that process just beginning. Dim galaxies, irregular shapes, fragile structures. The earliest building blocks of cosmic architecture only starting to come together. That is not what Webb found. Instead, it revealed galaxies that should not exist. Not in a philosophical sense, but in a concrete, physical one. Massive galaxies, bright galaxies. Galaxies already organized into recognizable structures. appearing when the universe was only 300 to 500 million years old. This discovery was not isolated. Webb has identified dozens of these systems, each confirmed through careful spectroscopic analysis, each presenting the same fundamental problem. They are too large, too bright, too structured, too early. According to our current models, these galaxies would have needed to form stars at rates that exceed what gravity should allow. Matter would have had to collapse and organize faster than known physical processes permit. The numbers simply do not work. Some of these early galaxies appear to contain as much stellar mass as our own Milky Way. But the Milky Way is more than 13 billion years old. It has had the entire history of the universe to accumulate its 100 billion stars. These distant systems achieved similar complexity in a tiny fraction of that time. Imagine watching a time-lapse video of a tree growing. You know from experience that a towering oak takes centuries to reach full height. Now imagine the footage shows a seedling becoming a mature tree in a single week. You would not doubt the video. You would doubt your understanding of how trees grow. That is where cosmology finds itself today. The observations are real. Multiple independent research teams have confirmed them. Webb is functioning exactly as designed. The instruments are behaving as expected. The measurements are solid. The galaxies exist. And their existence challenges the timeline we use to understand how the universe built itself. This is not a minor revision to theory. It is not a small adjustment to existing models. These galaxies suggest that something essential is missing from our picture of the early universe. Either matter behaved very differently in those first moments, or star formation proceeded far more efficiently than we believed possible, or our broader framework for cosmic evolution is incomplete. It may mean that the early universe was more dynamic, more extreme, and more efficient at building structure than our simulations predict. Or it may mean that key physical processes operated under conditions we have yet to fully understand. To grasp why these galaxies pose such a profound challenge, we need to step back even further, beyond the first stars, beyond the first galaxies, back to the very beginning, to the universe as it existed immediately after the Big Bang, when nothing yet resembled the cosmos we see today. The universe began in a state we can barely imagine: infinite density, infinite temperature, space and time themselves emerging from that singular moment, then expansion, rapid, violent, transformative expansion that continues to this day. For the first few 100,000 years, the universe was opaque, too hot for atoms to form. Matter existed as a plasma of free electrons and nuclei, scattering light in all directions. No structures, no stars, no galaxies. Just an expanding soup of elementary particles and radiation gradually cooling as space stretched. Around 380,000 years after the beginning, the temperature dropped enough for electrons to combine with nuclei. Hydrogen atoms formed. Helium atoms formed. For the first time, light could travel freely through space. This moment left an echo we still detect today, a faint microwave glow coming from every direction. The cosmic microwave background, our earliest baby picture of the universe. But even after this clearing, the cosmos remained dark. No stars had formed yet, no galaxies existed, just vast clouds of hydrogen and helium drifting through expanding space. Astronomers call this period the Dark Ages, and the name is literal. There was nothing to produce visible light. The universe was truly dark. Gravity was working, though, even then. Wherever matter was slightly more dense than its surroundings, that density attracted more matter. Dark matter, invisible but gravitationally powerful, began collecting into clumps. These clumps acted as seeds, drawing normal matter into their gravitational wells. Slowly, over millions of years, gas clouds collapsed inward. Eventually, in those densest regions, pressure and temperature rose high enough for nuclear fusion to ignite. The first stars were born. These weren't stars like our sun. They couldn't be. The early universe contained only hydrogen and helium, the lightest elements. No carbon, no oxygen, no iron. Stars that form from such pristine material behave differently than modern stars. They grow massive. Extraordinarily massive. Perhaps 100 times the mass of the sun or more. They burn incredibly hot and bright, and they live fast, dying in just a few million years. When these first stars died, they died violently. Supernovae. Explosions that scattered heavier elements into surrounding space. Carbon forged in stellar cores. Oxygen created through fusion. Silicon, magnesium, iron, all the building blocks of planets and ultimately life, spreading outward into the void. This element creation was crucial. The next generation of stars could form from gas enriched with these heavier elements. Smaller stars became possible. Planets became possible. The chemistry of the universe grew more complex with each stellar generation. But star formation alone doesn't create galaxies. Stars need to gather together. They need to be held in place by gravity. They need to organize into coherent structures. According to our models, this happened gradually. Very gradually. The first stars formed in isolation or small groups. These groups existed within larger dark matter halos, invisible scaffolding that provided the gravitational framework for structure formation. Over time, perhaps 50 to 100 million years, these small stellar groupings began to merge. Imagine droplets of water on a surface, each one slowly rolling toward others, combining into larger pools. That's how early proto-galaxies were thought to assemble. Collision, merger, gradual accumulation. Each merger took time. Each new combination had to settle into a stable configuration before the next merger occurred. The timeline we constructed from theory was clear. At 100 million years after the Big Bang, only the first stars should exist. Small clusters at best. By 200 million years, perhaps the earliest proto-galaxies. Tiny, irregular collections of stars. Nothing like the structured galaxies we see in the modern universe. By 500 million years, we expected to see slightly more developed systems, still small compared to modern galaxies, still irregular in shape, still in the early stages of assembly, perhaps a few million stars per galaxy, perhaps some early spiral structures beginning to form, but nothing massive, nothing fully developed. This hierarchical assembly model made sense. It matched what we observed in the modern universe. Large galaxies clearly form from the merger of smaller ones. We can see this process happening in real time when we observe galactic collisions. The Milky Way itself is currently absorbing smaller satellite galaxies. This is how cosmic structure builds. The model also matched our simulations. When astronomers input the known laws of physics into computer models and run the clock backward, they see this same pattern. Small structures first, larger structures emerging later. The mathematics of gravity, gas dynamics, and star formation all pointed toward gradual assembly over billions of years. Early galaxies in this framework should be fundamentally different from modern ones. They should be smaller, containing perhaps 1 million to a few tens of millions of stars. They should be dimmer, because they contain fewer stars, and those stars are young. They should be irregular in shape because they haven't had time to settle into the elegant spirals and ellipsoids we observe nearby. Most importantly, they should be rare. At 500 million years after the Big Bang, the universe simply hadn't had much time to build these structures. We expected to find a few early galaxies if we looked carefully enough. Perhaps a dozen or two in the deepest surveys. And we expected them all to be relatively modest. Everything in our theoretical framework pointed toward patience. The universe needed time to build complexity, time for stars to form and die, enriching the cosmos with heavy elements, time for gravity to pull matter together, time for small structures to merge into larger ones, time for the grand architecture of galaxies to emerge from primordial chaos. This wasn't speculation. It was built on decades of observation, careful measurement, and theoretical calculation. The model explained the cosmic microwave background. It explained the distribution of galaxies we observe today. It explained the abundance of light elements. It explained the large-scale structure of the universe. Armed with these predictions, astronomers pointed Webb at the deepest reaches of observable space. What the telescope returned changed everything we thought we knew. Webb's first deep field images arrived in the summer of 2022. Astronomers around the world waited for the data with measured anticipation. They expected beautiful images. They expected to see distant galaxies. They expected confirmation of the theoretical timeline. The images were indeed beautiful. Thousands of galaxies scattered across apparently empty patches of sky. Spirals and ellipticals in the foreground, more distant systems appearing as faint smudges of light. And beyond those, at the very edge of detection, tiny red dots. Those red dots were the problem. Red in astronomy means distant. Light stretches as it travels through expanding space. The longer the journey, the more it stretches. Visible light shifts into infrared. Infrared shifts to even longer wavelengths. This redshift serves as a cosmic clock, telling us how long ago the light began its journey. The reddest galaxies in Webb's images showed extreme redshift, light that left them when the universe was just a few 100 million years old. This alone wasn't surprising. Seeing galaxies from that era was exactly what Webb was designed to do. The surprise came when astronomers analyzed their properties. One galaxy, catalogued as Glass Z13, showed a redshift corresponding to roughly 300 million years after the Big Bang. Already remarkable. But spectroscopic analysis revealed something more troubling. The galaxy appeared to contain a substantial amount of stellar mass. Not millions of stars, billions of stars. A mass comparable to galaxies we observe in the modern universe. Another system, designated CEERS 93316, pushed even further back in time. Its light appeared to originate from the universe at just 250 million years old. And again, the mass estimates were staggering. This wasn't a small proto-galaxy slowly assembling. This was a mature system already containing billions of solar masses worth of stars. More discoveries followed. Each deep field observation revealed additional ancient giants. Galaxies at 400 million years, at 350 million years, some even earlier. All of them showing properties that contradicted expectations. These weren't measurement errors. Multiple independent teams analyzed the same galaxies using different methods. The results agreed. Spectroscopic confirmation followed photometric estimates. The redshifts were real. The distances were accurate. The galaxies genuinely existed in the early universe. But it was their brightness that first caught attention. These early galaxies shone with unexpected intensity. Brightness in astronomy correlates with stellar mass. More stars means more light. The brightness levels Webb detected suggested these galaxies contained stellar populations, far exceeding what theory predicted. When astronomers calculated the implied star formation rates, the numbers became even more problematic. To build such massive stellar populations in the available time, these galaxies would have needed to form stars at extraordinary rates. Not just high rates, rates approaching or exceeding the theoretical maximum for efficient star formation. Structure presented another puzzle. Some of these ancient galaxies showed organized morphology, disk-like features, central concentrations, signs of rotation. These are characteristics of mature galaxies that have had time to settle into stable configurations. They're not what you expect from systems still in their chaotic assembly phase. Spectroscopic analysis revealed additional complications. The light from these galaxies contained signatures of heavy elements: carbon, oxygen, evidence that multiple generations of stars had already lived and died. The universe at 300 million years old should have been dominated by pristine gas. Instead, these galaxies showed chemical enrichment that required substantial stellar processing. One particularly striking example appeared in a survey of a region called the Extended Groth Strip, a galaxy showing clear signs of maturity at a redshift corresponding to just over 400 million years after the Big Bang. Its spectrum revealed not just stars, but evidence of earlier stellar populations. This galaxy had history. It had experienced prior generations of star formation, enrichment, and evolution. The mass estimates kept climbing as more data arrived. Some of these early galaxies appeared to contain stellar masses equivalent to 100 billion suns. That's approaching the mass of our own Milky Way. But the Milky Way has had over 13 billion years to accumulate its stars. These systems accomplished similar feats in less than 500 million years. Time is the constraint that makes this impossible. Not impossible in a speculative sense, impossible according to the known physics of star formation and galactic assembly. Stars form when gas clouds collapse under gravity. This process has a maximum speed. Collapse too fast and pressure halts the process before stars can ignite. The gas needs time to cool, to fragment, to settle into stellar nurseries. Each step takes millions of years. Even assuming maximum efficiency, there's only so fast you can turn gas into stars. Calculate the maximum star formation rate for a given mass of gas, multiply by the available time, and you get an upper limit on stellar mass. For galaxies at 300 to 500 million years after the Big Bang, that upper limit falls well below the masses Webb observed. Some astronomers initially wondered if the mass estimates were wrong. Perhaps something about the early universe made these galaxies appear more massive than they actually were. But careful analysis ruled this out. The brightness, the spectroscopic features, the spatial extent of the galaxies all pointed toward genuinely massive stellar populations. Others suggested the redshifts might be incorrect. Perhaps these weren't early galaxies at all, but closer systems masquerading as distant ones through some unusual circumstance. This too failed scrutiny. The spectroscopic redshifts were unambiguous. The patterns of absorption and emission lines clearly indicated extreme distances. The data was solid. The observations were reliable. Multiple independent lines of evidence confirmed the same conclusion. These massive, structured, chemically enriched galaxies existed when the universe was young. Too young for such systems to have formed according to our understanding of cosmic evolution. Each new Webb observation added more examples. The sample size grew. The pattern became undeniable. This wasn't a handful of unusual objects. This was a population. These early giants represented a genuine class of galaxies that our theories had failed to predict. And if they exist, if they formed in the time available, then something fundamental about our understanding must be incomplete. These observations don't just tweak our models. They fundamentally challenge the physics of how matter assembles in the early universe. To grasp the full magnitude of this problem, we need to understand what it actually takes to build a galaxy. Galaxy formation begins with dark matter. This invisible substance doesn't emit light. It doesn't interact with normal matter except through gravity. But that gravitational interaction is everything. Dark matter outweighs normal matter by roughly 5 to 1. In the early universe, it clumped first, creating gravitational wells that normal matter fell into. Think of dark matter as the scaffolding, the invisible framework that gives structure to the cosmos. Without it, galaxies as we know them wouldn't exist. These dark matter halos formed gradually. Quantum fluctuations in the infant universe created tiny density variations. Regions slightly denser than average attracted more matter. That extra matter increased the gravitational pull, attracting even more matter. A feedback process that amplified over time. But even with this gravitational amplification, the process took time. Millions of years for the first small halos to collapse. Tens of millions more for them to merge into larger structures. The mathematics of gravitational collapse is well understood. There's a minimum timescale involved. You can't compress matter faster than gravity can pull it together. Once dark matter halos formed, normal matter could begin accumulating. Hydrogen and helium gas fell into these gravitational wells, heating as it compressed. This is where the second constraint appears. Hot gas doesn't easily form stars. It needs to cool first. Cooling happens through radiation. Gas atoms collide, transferring kinetic energy into photons that escape into space. As the gas radiates away its energy, it cools and contracts further. Eventually, it becomes dense and cool enough for stars to form. In the modern universe, this cooling process benefits from the presence of heavy elements. Carbon and oxygen are particularly efficient at radiating energy. They act as cosmic coolants, allowing gas to shed heat quickly. But the early universe lacked these elements. Only hydrogen and helium existed initially. These elements cool much less efficiently. This creates a fundamental bottleneck. Early universe gas takes longer to cool. Longer cooling times mean slower star formation. Slower star formation means galaxies build their stellar populations gradually, not rapidly. Even once gas cools enough, star formation itself has limits. When a dense cloud fragments into stars, those stars begin affecting their environment immediately. Young, massive stars emit intense ultraviolet radiation. This radiation heats surrounding gas, making it harder for new stars to form nearby. The process regulates itself. Stellar winds add another layer of regulation. Hot stars blast powerful streams of charged particles into space. These winds push gas away from star-forming regions. Material that could have become stars gets expelled instead. Then come supernovae. When massive stars die, they explode with tremendous energy. Each supernova injects heat and momentum into the surrounding medium. Gas that was collapsing to form new stars gets blown outward. Star formation in that region halts until the gas can cool and collapse again. This cycle of collapse, star formation and disruption means star formation proceeds in bursts, not as a continuous process. These feedback mechanisms prevent runaway star formation. Without them, galaxies would convert all their gas into stars almost instantly. But feedback makes star formation self-limiting. There's a maximum rate at which any given mass of gas can form stars. Push beyond that rate and feedback processes shut down star formation entirely. Astronomers have measured this maximum rate in nearby galaxies. In the most extreme starburst galaxies where conditions are optimal, star formation reaches perhaps a few hundred solar masses per year. That sounds like a lot, but remember, these are the most efficient star-forming galaxies we observe. Most galaxies form stars far more slowly. The Milky Way, for reference, currently forms roughly 1 to 2 solar masses worth of stars each year. Over its entire lifetime of more than 13 billion years, that accumulated into roughly 100 billion solar masses of stars. Simple multiplication. Time multiplied by rate equals total mass. Now consider the early universe galaxies Webb observed. Some contain stellar masses approaching 100 billion solar masses, but they existed when the universe was just 3 to 500 million years old. To accumulate that much stellar mass in that time requires formation rates far exceeding what we observe anywhere in the modern universe. Calculate the required rate. 100 billion solar masses divided by 500 million years equals 200 solar masses per year. Sustained, constantly, for the entire half-billion-year period. No pauses, no feedback regulation slowing things down. Just continuous maximum efficiency star formation from the moment the universe allowed it until the moment we observe these galaxies. That's the absolute minimum rate. It assumes perfect efficiency. It assumes every bit of available gas converts into stars. It assumes no material is lost to winds or supernovae. These assumptions are unrealistic. In practice, star formation is much less efficient. Most gas doesn't become stars. It gets heated, blown away, or remains unconverted. Account for realistic efficiencies, and the required formation rates climb even higher. Perhaps 500 or 1,000 solar masses per year. Sustained for hundreds of millions of years. Rates that exceed even the most extreme starburst galaxies we observe today. There's another problem: heavy elements. The spectra from these early galaxies show evidence of carbon, oxygen, and other elements beyond hydrogen and helium. These elements don't exist naturally. They must be created inside stars and distributed through supernovae. Creating significant quantities of heavy elements requires multiple generations of stars. The first generation forms from pristine gas, lives, and dies, scattering heavy elements. The second generation incorporates those elements, creates more through fusion, and distributes them through additional supernovae. Only after several such cycles does the abundance of heavy elements reach the levels Webb observed in these early galaxies. Each stellar generation takes time. Massive stars that create heavy elements live only a few million years, but then their ejecta must mix into the surrounding gas. New stars must form from that enriched material. Those stars must live and die. The cycle repeats. Even rushing through this process optimistically requires tens to perhaps 100 million years. That leaves even less time for the bulk of star formation. If the first 100 million years goes to creating and distributing heavy elements through early stellar generations, and the universe is only 400 million years old when we observe the galaxy, just 300 million years remain for building the bulk of the stellar mass. The required formation rates climb even higher. Then there's the energy budget. Star formation requires compressing gas. Compression heats gas. That heat must be radiated away. All this requires energy. The energy has to come from somewhere. In the early universe, the primary energy source is gravitational collapse. But gravitational energy release happens at a finite rate. There's only so much energy available in a given time. Calculate the energy needed to form 100 billion solar masses worth of stars in a few 100 million years. Compare that to the energy available from gravitational collapse of gas into dark matter halos. The numbers strain plausibility. You're asking the universe to operate at or beyond maximum theoretical efficiency for hundreds of millions of years without pause. The physics simply doesn't permit what Webb observed, not with our current understanding, not with the laws of gravity, thermodynamics, and stellar evolution as we know them. The observations and the theory exist in contradiction. Faced with observations that seem to violate physical law, astronomers have proposed several possibilities. Each reveals something profound about the limits of our understanding. When observations conflict with theory, scientists face a choice: question the observations or question the theory. In this case, the observations appear sound, which leaves theory open to revision. The first possibility considers star formation efficiency. Perhaps conditions in the early universe allowed gas to convert into stars more readily than it does today. The lack of heavy elements, usually considered a hindrance, might have created unexpected advantages. Without heavy elements, early gas clouds couldn't cool as efficiently through radiation. But perhaps this forced them to fragment differently. Larger fragments might have formed, creating more massive stars. More massive stars means more light per unit mass. The galaxies might appear brighter than expected without actually containing as many stars as we estimate. This explanation has appeal. It requires no new physics, just different conditions leading to different outcomes. Star formation efficiency varies in the modern universe. Why not in the early universe too? The problem lies in the details. More massive stars live shorter lives. They burn through their fuel in just a few million years. To maintain the observed brightness over hundreds of millions of years requires continuous formation of new, massive stars. That brings us back to the rate problem. You still need to form stars faster than feedback mechanisms should allow. Additionally, very massive stars create heavy elements efficiently. If the early universe formed predominantly massive stars, we'd expect to see even more heavy element signatures than we do. The observations don't support this. A second possibility involves dark matter behavior. We know dark matter exists, we observe its gravitational effects, but we don't know what it actually is. Perhaps dark matter particles in the early universe behaved differently than they do today. If early dark matter clumped more efficiently, it could have created stronger gravitational wells earlier. Deeper wells would pull normal matter in faster. Faster collapse could accelerate star formation. The timeline compression might be explained by enhanced dark matter clustering in the young universe. This hypothesis encounters its own difficulties. We have very good observations of the cosmic microwave background. That ancient light carries information about density fluctuations in the early universe. Those fluctuations tell us how matter, including dark matter, was distributed. The patterns we observe match our standard models well. Modified dark matter behavior would alter those patterns. We don't see the alterations this explanation requires. A third approach points to supermassive black holes. Modern galaxies typically host enormous black holes at their centers, millions or even billions of times the mass of the Sun. These black holes influence their host galaxies profoundly. Material falling toward a central black hole releases tremendous energy. That energy can trigger star formation in surrounding gas. Perhaps early galaxies formed around seed black holes. These seeds could have assembled quickly, even before significant star formation occurred. Once in place, they might have catalyzed rapid galaxy growth. The black hole's gravity attracts gas. The energy from infalling material triggers star formation, a feedback loop that accelerates galaxy assembly. This idea faces a chicken and egg problem. How do you form supermassive black holes in the early universe? Black holes form from stellar collapse or from direct collapse of massive gas clouds. Either route takes time. Stellar collapse requires stars to form first, live, and die. Direct collapse requires very specific conditions that may be rare. Even if seed black holes form early, they need time to grow. Black holes grow by accreting matter. Accretion happens at a finite maximum rate determined by the physics of how matter spirals inward. Grow a black hole too fast, and radiation pressure from infalling material pushes new material away. The black hole chokes off its own growth. Calculate how quickly a black hole can grow from stellar mass to millions of solar masses. The timescales don't easily fit within the few 100 million years available. You encounter similar compression problems as with star formation itself. Some astronomers have proposed that population 3 stars, the very first stellar generation, were more efficient at creating heavy elements than we thought. These pristine stars formed from hydrogen and helium alone. If they were predominantly very massive, they would have created and distributed heavy elements quickly. Rapid element enrichment would allow subsequent star formation to proceed more efficiently. Heavy elements aid cooling. Better cooling means faster star formation. Perhaps this acceleration explains what Webb observed. But again, the timescales pose challenges. Even very massive population 3 stars need a few million years to live and die. Their ejecta need time to mix into the surrounding medium. New stars need time to form from that enriched gas. Stack these sequential processes and you still struggle to fit everything into the available time window. Moreover, if population 3 stars were ubiquitous and very massive, we'd expect to see their signatures in various astrophysical observations. We don't see strong evidence for a massive population 3 star era. Their effects appear more subtle than this explanation requires. The most radical possibility questions the cosmological model itself. Our standard model, called lambda CDM, describes a universe dominated by dark energy and cold dark matter. It includes specific parameters for expansion rate, matter density, and cosmological constant. These parameters were determined through decades of careful observation. Lambda CDM has been remarkably successful. It explains the cosmic microwave background. It explains the large-scale distribution of galaxies. It explains the acceleration of cosmic expansion. It matches observation after observation. But perhaps it's wrong in subtle ways. Perhaps the early universe evolved differently than lambda CDM predicts. Maybe the expansion rate was different. Maybe matter was distributed differently. Maybe some aspect of physics we don't understand played a role in early cosmic evolution. This is the most unsettling option because it undermines our most fundamental framework. If lambda CDM fails to describe the early universe accurately, then many conclusions built on that foundation become uncertain. The age of the universe, the timeline of structure formation, the nature of dark energy and dark matter. All of it becomes questionable. Revising cosmological models isn't unprecedented. We've done it before when observations demanded it. But it's never comfortable. Entire careers are built on frameworks that suddenly need reconsideration. And there's a deeper issue. Even if we modify lambda CDM, we still need to explain the physical mechanisms. It's not enough to say the model was wrong. We need to specify what was wrong and why. We need new physics that predicts the observations while remaining consistent with everything else we know. None of these explanations fully resolves the paradox. Each addresses part of the problem while creating new difficulties. Modified star formation efficiency requires rates that strain physical limits. Different dark matter behavior conflicts with other observations. Seed black holes face their own formation timeline problems. Enhanced population 3 enrichment still requires time we don't have. Modified cosmology demands new physics we haven't identified. The truth might involve combinations of these factors. Perhaps star formation was moderately more efficient, and dark matter clustering was slightly enhanced, and early black holes contributed somewhat to galaxy growth. Stack several small effects and maybe they explain what Webb sees. Or perhaps none of these approaches capture what's actually happening. Perhaps we're missing something entirely. Some process or phenomenon we haven't considered because we've never encountered conditions like the early universe provides. Beyond the specific theories, these discoveries force us to confront uncomfortable questions about the nature of scientific knowledge itself. About what happens when reality refuses to cooperate with our most elegant equations. Lambda CDM has been the standard model of cosmology for decades. The name describes its components. Lambda represents dark energy, the mysterious force accelerating cosmic expansion. CDM stands for cold, dark matter, the invisible scaffolding that holds galaxies together. Together with normal matter and radiation, these components form our picture of the universe. This model emerged gradually through observation and theory. In the late 20th century, astronomers measured the cosmic microwave background with increasing precision. They mapped the distribution of galaxies across vast volumes of space. They observed distant supernovae to track cosmic expansion. Every measurement refined the model's parameters. By the early 2000s, Lambda CDM had become remarkably precise. We could specify the universe's composition to within a few percent. Roughly 68% dark energy, 27% dark matter, 5% normal matter. The expansion rate, the age of the universe, the geometry of space, all determined with impressive accuracy. The model's success came from its predictive power. Tell Lambda CDM the conditions in the early universe, and it predicts the cosmic microwave background patterns we observe. Input the matter distribution, and it predicts how galaxies cluster. Ask about cosmic expansion, and it matches supernova observations. Success after success built confidence. But models are only as good as the observations that test them. Lambda CDM was tested primarily against the modern universe and the cosmic microwave background from 380,000 years after the Big Bang. The intervening period from the Dark Ages through the first billion years remained largely theoretical. We had models for that era but limited observational tests. Webb has changed that. For the first time, we're directly observing the universe during that critical early period. And what we see doesn't match expectations perfectly. This isn't necessarily a crisis. Models evolve. Science progresses by refining theories when new data arrives. But the galaxy observations suggest something more fundamental than simple parameter adjustment. If these massive early galaxies are real and common, they imply the early universe could assemble structure more efficiently than Lambda CDM predicts. That efficiency might come from modified initial conditions. Perhaps matter was distributed slightly differently than we thought. Perhaps the density fluctuations from the Big Bang had characteristics we didn't account for. Or the efficiency might come from missing physics. Lambda CDM includes gravity, expansion, known matter, and energy. But it assumes we understand how these components behave at extreme conditions. The early universe was hot, dense, and unlike anything we can recreate in laboratories. Perhaps matter behaves differently under those conditions. Dark matter presents particular uncertainty. We know it exists from gravitational effects. We don't know what particles compose it. We don't know if it interacts with itself. We don't know if its properties change with temperature or density. Lambda CDM makes assumptions about dark matter behavior. If those assumptions fail in the early universe, predictions fail too. Dark energy adds another layer of mystery. We observe its effects on cosmic expansion. We don't understand its nature. Lambda CDM treats dark energy as a constant, a fixed property of space itself. But what if dark energy evolved over time? What if its strength was different in the early universe? Different dark energy behavior would alter structure formation timelines. There's also the possibility of entirely unknown components. Physics operates in regimes we've never accessed in the early universe. Energies far beyond particle accelerators, densities that compress matter in ways we can't replicate. Perhaps under those conditions, phenomena emerge that play no role in the modern universe. Consider an analogy. Imagine scientists studying water only at room temperature. They develop a comprehensive model of liquid behavior. Then someone shows them ice. The molecules are the same. The fundamental physics hasn't changed. But organized differently, water exhibits completely new properties. Their model didn't predict ice because they'd never observed the conditions where it forms. Perhaps we're in a similar situation. Our cosmological model works beautifully for the universe we can observe directly. But the early universe operated under conditions so extreme that new phenomena emerged. Phenomena with no modern analogues. Webb might be showing us cosmic ice when we only modeled cosmic water. Historical precedent suggests caution about declaring cosmological crises. Astronomers have encountered puzzling observations before. In the mid-20th century, radio astronomy revealed powerful sources that didn't match any known objects. Quasars initially defied explanation. Eventually, we understood them as supermassive black holes in distant galaxies. No crisis, just new phenomena requiring new understanding. Similarly, the accelerating expansion of the universe came as a surprise in the late 1990s. It required introducing dark energy, a completely unknown component. This was shocking, but not a failure of cosmology. Rather, it was a discovery that expanded our understanding. Webb's galaxies might follow this pattern. Not a failure of lambda CDM, but a discovery of processes the model didn't include. Perhaps massive early galaxies form through mechanisms we haven't considered. Perhaps rare conditions in the early universe created these systems without requiring fundamentally new physics. But we must also consider the possibility of genuine model failure. Not every anomaly resolves neatly. Sometimes observations reveal that our framework was incomplete or incorrect. The transition from Newtonian gravity to general relativity didn't come from tweaking parameters. It required reconceptualizing space, time, and gravity itself. If lambda CDM proves inadequate for the early universe, revising it won't be simple. The model is deeply interconnected. Change one component and ripple effects propagate throughout. Modify early structure formation and you affect predictions for cosmic microwave background patterns, galaxy evolution, chemical enrichment, everything that follows. Any revision must also preserve lambda CDM's successes. The model correctly predicts many observations. New frameworks must explain what lambda CDM explained, while also accounting for early massive galaxies. That's a demanding constraint. There's an epistemological question underlying all this. How well can we know the early universe? We observe ancient light that traveled billions of years to reach us. We can't repeat the observations with controlled experiments. We can't access the conditions directly. We build models based on extrapolating known physics to extreme regimes. That extrapolation might be reliable. Physical laws appear universal. Atoms in distant galaxies behave like atoms on Earth. Gravity operates the same everywhere we've tested it. This universality gives us confidence. But confidence isn't certainty. We assume physics doesn't change across cosmic time. We assume the laws we've measured in laboratories and nearby space apply equally in the early universe. These assumptions might be correct. They might also be subtly wrong in ways that only matter under extreme conditions we rarely encounter. Webb forces us to test assumptions we previously took for granted. It provides direct observation where we previously had only theory. This is valuable regardless of whether it confirms or challenges our models. Either outcome advances knowledge. If Webb confirms lambda CDM, we gain confidence in our framework. If it reveals cracks, we gain opportunities to develop deeper understanding. Both paths lead forward. As we stand at this threshold of uncertainty, these ancient galaxies offer us something more valuable than answers. They remind us that the universe still holds the power to surprise us, to humble us, and to invite us deeper into mystery. Light from these ancient galaxies began its journey over 13 billion years ago. When that light departed, the universe was young. Earth didn't exist. The sun didn't exist. The Milky Way was still assembling from smaller fragments. Life hadn't emerged anywhere we know of. The photons traveled through expanding space for eons. They passed through voids between galaxy clusters. They crossed vast stretches of intergalactic medium. They journeyed while stars were born and died, while galaxies collided and merged, while the universe gradually transformed from its infant state into the cosmos we inhabit. And then, after all that time, those ancient photons encountered a gold-plated mirror orbiting between Earth and the Sun. They reflected into detectors. They were converted into data. They traveled as electronic signals to astronomers who decoded them, analyzed them, and recognized their profound implications. We are looking at light from the universe's childhood. Not metaphorically, actually. The galaxies we see through Webb existed when cosmic history was just beginning. And somehow, across all those billions of years and trillions of miles, information about those early times reached us intact. That we can do this at all is remarkable. That we can measure redshifts, estimate masses, detect chemical compositions, all from light that traveled for such vast distances, speaks to both the precision of our instruments and the reliability of physics itself. Light carries information faithfully across cosmic distances. Physical laws remain constant. The universe is knowable. But knowable doesn't mean known. These early galaxies reveal gaps in our understanding. They show us that despite decades of progress, despite increasingly sophisticated observations, despite elegant theoretical frameworks, nature still holds surprises. This is not a failure, it's an invitation. Science progresses through exactly this pattern. Observation reveals something unexpected. Theory struggles to explain it. New ideas emerge, some fail, others gain support. Understanding deepens. The process repeats. Each cycle builds on previous knowledge while occasionally overturning assumptions we thought were secure. The massive early galaxies Webb discovered might ultimately fit within our existing framework. Perhaps we're missing subtle effects that, once included, reconcile observation with theory. Perhaps star formation in the early universe operated at higher efficiency than we estimated. Perhaps dark matter clustering proceeded faster than models suggested. Perhaps several small effects combined to create the observed outcome. Or perhaps these galaxies signal something more fundamental. Perhaps they're teaching us that the early universe operated differently than we imagined. not through different physical laws, but through conditions so extreme that they accessed regimes of physics we don't yet understand. Either possibility offers value. Confirming our models strengthens confidence in our understanding. Revising our models opens doors to new physics. Both paths advance knowledge. Webb will continue observing. More deep fields are planned. Longer exposures will reach even earlier times. Spectroscopic surveys will provide detailed information about hundreds of early galaxies. The sample size will grow. Statistical patterns will emerge. Some questions will be answered, and undoubtedly, new questions will arise. That's how exploration works. Every answer illuminates nearby areas previously shrouded in darkness. And in that newly illuminated space, we see things we couldn't have imagined before we looked. The early massive galaxies might represent rare circumstances rather than typical conditions. Perhaps we're observing special environments where convergence of unusual factors allowed rapid galaxy assembly. The universe is vast. Rare events become common somewhere when you survey enough volume. Or perhaps these galaxies aren't actually as massive as they appear. Perhaps some systematic effect makes them look brighter or more massive than they truly are. More detailed analysis might revise the mass estimates downward, easing the tension with theory. Or perhaps they're exactly what they appear to be. Massive, mature galaxies existing impossibly early. Objects that demand we reconsider fundamental assumptions about cosmic evolution. Time will tell. Astronomy operates on long timescales. Decades can pass between a puzzling observation and its explanation. The nature of quasars remained mysterious for years. The cause of gamma-ray bursts eluded understanding for decades. Eventually, through patient observation and careful analysis, answers emerged. The massive early galaxies will likely follow a similar trajectory. More data will accumulate. Competing explanations will be tested against observations. Some will be ruled out. Others will gain support. Gradually, consensus will build around an explanation that fits the evidence. That explanation might require minor adjustments to our models. It might require major revisions. It might require entirely new physics. We don't know yet. And that uncertainty is itself a kind of gift. In an age when we can answer many questions with quick searches, when information flows freely, when knowledge accumulates rapidly, genuine mystery becomes rare and precious. These early galaxies present us with a mystery that can't be resolved through clever argumentation or database queries. Only patient observation and careful reasoning will reveal their secrets. They remind us that the universe is not obligated to make sense on our timescales or according to our expectations. It simply is. It follows its own rules, operates according to its own logic. Our task as observers is to watch carefully, measure precisely, and adjust our understanding when reality demonstrates we were mistaken. This humility before nature is essential to science, not false humility that denies what we do know, not excessive skepticism that questions everything including well-established facts, but genuine openness to the possibility that our current understanding, while substantial and hard-won, remains incomplete. The atoms in your body were forged in stars. Carbon, oxygen, nitrogen, calcium, iron, all created through nuclear fusion in stellar cores and distributed through supernova explosions. You are literally made of stardust. This isn't poetic metaphor. It's documented physical reality. Those stellar furnaces operated according to the same physics that governs the early galaxies Webb observes. The same gravity that pulled ancient gas clouds together operates on Earth today. The same electromagnetic forces that bound atoms in the early universe bind the molecules in your cells. We are part of this cosmic story, not separate observers examining the universe from outside. Participants in the same grand narrative that began 13 billion years ago and continues now. The mystery of the early massive galaxies is our mystery. Their story is part of our story. And that story, it seems, is stranger and more wonderful than we ever imagined, more complex than our theories predicted, more surprising than our simulations suggested, more beautiful in its refusal to conform to expectation. The light from those ancient galaxies continues to arrive. Every moment, more photons complete their 13 billion year journey. Each one carries information from a time when the universe was young and different. Each one offers a glimpse into cosmic history. We've only begun to read what they're telling us.